Right, good morning, guys. I'll wait like one more minute, then we'll make a start. Oh, sorry, my mic was off then. Um, right, so let me just give you a quick recap. We previously talked about all the different energy stores, and we'd done two sets of calculations previous. So there's many different types of energy stores, such as chemical, gravitational, kinetic, elastic, nuclear, all of that. But we're only focusing on how to calculate the energy store in three different types of energy store. So we're only going to calculate for three. The first one we calculated was gravitational potential, and that formula was mgh. M being mass, G being gravitational field strength, and H being the height from the ground. Then we looked at kinetic energy, which was Ke equals 0.5 or a half mv squared. Remember, the squared belongs only to the v, the velocity. It's not squaring the whole thing. That's one mistake that I do see. Sometimes the square is only squaring the velocity bit. Now we're going to move on to an equation that is actually going to be given to you. So on your real GCSE exams and also on topic tests we do in class, this equation will be given, so you don't need to memorize it. Oftentimes though, you're given like an equation list. So even though you don't need to memorize the equation, you still need to be able to pick out that this is the equation I have to use. So know the equation in that you know that this is the elastic potential energy equation, but you don't need to memorize every single part of it. You do need to memorize gravitational potential energy and the kinetic energy equations though. So for the elastic potential energy equation, we have several sort of new parts to it, like we have for gravitational potential energy and kinetic energy, we're working with things like mass, which you guys already know. We've explained gravitational field strength as how strong the gravity is in a particular planet or place. V is just the speed or the velocity. But now with the elastic potential energy, there's these new terms that I do want to be able to define first. So the equation, I'm going to write EPE for elastic potential energy, is equal to 0.5 KE squared. Remember, it's 0.5 times K times E squared. Because in algebra we don't usually write the time symbols there. Okay, now I'm going to explain all the different parts to this equation. So let's rewrite it again, nice and big down here. Right, so elastic potential energy. What it is specifically is the energy. Yes, there is. It should be on the website down here, but the main notes is just like a calculations notes. It's just a formula and then the notes. There's no like actual proper notes because it's mainly the maths. So elastic potential energy you already written this down during our first session, but it's the energy stored when something is stretched or squashed. We often forget about that second one. So you guys can already think of elastic potential energy as, you stretch an elastic band, you're increasing the elastic potential energy store of that elastic band. But let's say you had a spring and you squash the spring down, that's still storing elastic potential energy. So you can store elastic potential energy by sort of changing its actual shape itself by either stretching it or squashing it. Now, the 0.5 is just a number that you have to times on. Now here's this new one called K. Oh, also, forgot to mention, remember, because elastic potential energy is an energy, it's going to be measured. Energy is always measured in joules or shortened to J. Now K is something that's known as the, let me do it in a different color, spring constant. The unit for that is newtons per meter. What the spring constant is let's imagine that you had two elastic bands. There's my first elastic band, there's my second elastic band. In terms of their size, Let's say they're exactly the same. So size exactly the same, length exactly the same. Now let's pretend that I had a machine that could stretch it using an exact force. Like I set my machine to say, right, now give me 5 newtons of force. So I'm going to use my machine and stretch this rubber band, this elastic band, with 5 newtons of force, and I'm going to do the exact same with the other one. Well, the two elastic bands, they might not stretch the exact same distance. Even though they're the same size, one may be stretchier than the other. So let's say that the first elastic band stretched just a little bit more after I put my 5 newtons of force, but my second elastic band stretched by a whole lot. The only difference between these two elastic bands, if their mass was the same, if their starting length was the same, I've applied the same amount of force to both of them. The only difference between these two elastic bands is what's known as the spring constant, which is basically a measure of stretchiness, to put it plainly. It's how stretchy something is, and that's going to affect how much elastic potential energy is stored. The bigger the number, it means it's less stretchy. This might seem a little bit like counterintuitive, but if you think about the unit, let's say we had we applied the 5 newtons of force to each of them. Let's say the first elastic band only stretched by 1 meter. And then the second elastic band stretched by 5 meters. Well, the first elastic band would then have a spring constant of 5, because 5 divided by 1. The second elastic band would have a spring constant of 5 divided by 5 is 1. So, if you look at just this bit here, the first one stretched by very, very little with 5 newtons of force, and it ended up with a spring constant score of 5. The second one stretched a lot with 5 newtons of force, and it ended up with a spring constant of 1. So basically, if you have a bigger number of a spring constant, that means it's less stretchy. If you have a smaller number, that means it's going to be more and more stretchy. Now, one thing interesting to think about is if it's possible to have something with a spring constant of 0, meaning it's like infinitely stretchy. Well, in reality, this probably wouldn't be possible, but if we were like engineers trying to design something that is as stretchy as possible, we're trying to get as close to 0 as possible for maximum stretchiness. So it is possible to get something like 0.00001 spring constant, but it's going to be really hard to get something to 0, because that means it's like perfectly stretchy. If you kept stretching it, it would just keep extending and never snap, which makes no sense in reality, but it provides a number for us to move down to when we're trying to design elastic materials. So the spring constant is just basically a measure of how stretchy the material is. Now E in my formula, E stands for the extension or compression. So basically, how much did it get stretched or squashed by? So let's say that I had a spring. There's my spring there. Let's say that it started off at 0.5 meters, and then I stretched it out, and now it's a total length of 0.7 meters. That means my extension is going to be how much it's stretched by. It's going to be the increase. So my increase was 0.2 meters. One mistake that a lot of students make is just putting the overall lengths in there, like they would put in 0.7 into the formula as a total new length. But you do have to be aware that the E in our elastic potential energy formula, this is the change, not the new length, not the old length. It's the change in the length, and that's going to be measured in meters. So if you have something in, say, centimeters, you have to make sure you divide by 100 first and change it into regular meters. Okay, let's do some examples. I have here two examples. So my formula, I'll write just up here, EPE equals 0.5 KE squared. When it comes to these calculations, you're still using the Fifo method. The Fifo method applies to pretty much all of calculations using a formula in physics. The only difference is you might have to work out an additional value. So for example, in this case, we have to work out the extension because the question gave us the starting length of the unstretched spring and the final length of the unstretched spring, but it didn't give us the extension itself. So we have to work that out. So if it started off unstretched 0.5 meters and then stretched to 1 meter, that means my extension was how much it grew by, and that's going to be it grew by another 0.5. My elastic potential energy, that's what I'm trying to find. So right now all I'm doing is just making a list of all my values, and my spring constant they gave me was 150. Newtons per meter. So those are all my values. The only extra thing I had to work out was the extension from the picture. So it's just the actual change itself. I'm not taking any of these default values straight off the bat. I'm doing the actual change in the extension, in the length. So if we plug it into our formula, EPE is equal to 0.5 times K, which is my spring constant, so it's going to be times 150 times E squared, which is extension squared. So that's 0.5 squared. Remember, the squared only belongs to the extension. It's not that you're squaring the whole thing. So depending on how good your calculator is, you can maybe chuck the whole thing into your calculator and then get an answer. Or if you have a less powerful calculator, you need to do it in parts, that's fine too. I'm using the computer calculator, so I gotta do it in parts. So 0.5 times squared, 0.5 squared and then I'm just gonna times all of those together. Check on your own calculator to make sure that you're able to get the same answer. I got 18.75 joules. So just check that you're getting that answer. Okay. So that is the elastic potential energy equation. We start off with 0.5 because that's just part of the formula. We times it by the spring constant, which is how stretchy something is. And then we're going to times it with the squared value of the extension. Now here's my second example. In this case, it's a compression. Even though it got compressed instead of extended, the E value is still going to be the E value. Instead of just being an extension, we're just going to use the change in length still. So the extension this time, the change in length is it went from 75, got squished down to 49. So the change in length is just going to be 75 minus 49. Oops. So that's 26. So the extension is 26 centimeters, but remember, I have to have that in meters. So to change from centimeters to meters, you just divide by 100, 0.26 meters. My elastic potential energy, that's what I want. And my spring constant equals 195. That was just given to me here. So once again, I just substitute everything into the formula. I don't have a value for elastic potential energy. My next bit is EPE equals 0.5 times the spring constant, 195, times the extension, or in this case a compression, 0.26 squared. That squared only belongs to the 0.26. So once again, chuck that in your calculator. I got if I round it, 6.6 joules. So hopefully we all managed to get that. Okay, now I'm gonna do a more challenging one. A stretch spring, this is just gonna be an example. A stretch spring has a total length of 20 centimeters and a spring constant of 200 newtons per meter. It is storing 0.25 joules in its elastic potential energy store. Determine the unstretched length of the spring. Now I'm going to show you the Fifo method when you're doing it in a question, because obviously, like as I've shown you on the notes booklets, it's already divided into sections for you. But now I'm going to model it as to what will it look like when you answer a question. The very first thing, remember, is to go through each part of the question from left to right, and anytime they give you a value or ask you to find the value, you write that down. So a stretched spring has a total length of 20 centimeters. Well, that's a value they've given me. and that's a stretched length, because it says a stretched spring has a total length. So I'm going to say stretched length equals 20 centimeters, and I already know that I'm going to have to change that centimeters to meters. Divide 20 by 100, and you get 0.2 meters. And a spring constant of 200 newtons per meter. So that's another value they've given me. I'm going to write that out. Spring constant equals 200 newtons per meter. It is storing 0.25 joules in its EPE store. EPE equals 0.25 joules. Determine the unstretched length of the spring. So unstretched length equals question mark. So basically what this question's asking me to find out is its extension, because if I know its new stretched length and I knew its extension, I can then work out what the original length was. Because I know its new length, I know how much it stretched by, I could just then work backwards and subtract to find the original length. First, Fifo method, the first F stands for formula. Remember, this bit helps with being able to substitute in later on. Right, now that I have my formula written out, I'm going to look at each value in the formula and see if there's something in my list I can substitute in. So EPE, I check my list, I do have a value for EPE, that's 0.25, is equal to 0.5. K is spring constant. I'm checking my list to see if I have a value for spring constant. That's 200. I do have a value. Times E squared. Now E, remember, is the extension. I have the new stretched length, but that's not an extension. It's just the new length that it is. Now this is where a lot of students make the mistake, in that they would just chuck in the stretched length into the formula, but remember, E is the extension or the compression. It's not the new total length. So I don't actually know what my extension is, so I'm going to leave it as E. Then remember, in any sort of FIFA bit, we've done the formula, we've inserted the values, we already got a mark for that. Now we're going to fine-tune it by just rearranging, cleaning it up a bit. Remember that the very first step in fine-tuning is just seeing if there are any numbers that you can combine to just seeing if there are any numbers that you can combine together to make one number, because otherwise it'll be kind of tough trying to rearrange with multiple numbers about. So I noticed that the 0.5 times 200, I could probably just turn that into one number by actually calculating that out, what 0.5 times 200 is. If I pull up my calculator, 0.5 times 200 is 100. So all I've done is just change that bit into one number. Now it looks a bit cleaner. We're trying to solve for the extension, because that's the missing variable. So remember, we have to isolate it, just like you do in maths, by moving everything to the other side. So I have E squared here, but I have it 100 times dawn. So I want to get rid of that 100 by doing the opposite. Because that 100 is times dawn, I can divide by 100. And just like in maths, the hundreds cancel out. But remember, anything I do on one side, I have to do on the other side. So I'm dividing both sides by 100. Now, gonna stick the 0.25 divided by 100 into my calculator. That gives me 0.0025 is equal to E squared. But remember, I need extension. I don't want extension squared, so I'm not actually done yet. In order to get just the E, I have to do the opposite. Because it's E squared, to get rid of the squared, I can square root it. And anything I do on one side, I have to do on the other. So my final answer is going to be 0.0025 square rooted, and that is 0.05 meters is equal to my extension. So I know that my spring stretched by 0.05 meters. I know that it's stretched to become 0.2 meters. Let me change the color here a bit. So the original unstretched length stretched by 0.05 and made 0.2. So this is what I meant by we can easily then work backwards to figure out what my unstretched length is. So, can anyone tell me what would be my original length if I know that it's stretched by 0.05 and it's stretched to become 0.2? What was the original unstretched length? Yeah, spot on. So the original unstretched length would have been 0.15 meters because 0.15 added on 0.05 is equal to 0.2. All you had to do was just subtract the new length from subtract the extension from the new length to figure out what it originally was. Okay, let's do we'll do another example. Well, I'll let you guys do this one and then see where we're at. So this is on the website in the same conservation and dissipation of energy booklet that we have been using. This is going to be side by side. So I have an example written out for you guys here for you to try to follow, to do each step alongside it to help you structure it a bit. So this is the one that I want you guys to do. A spring with a spring constant of 520 newtons per meter stores 7.04 joules. How far is it extended from its original position? So list all the values, write the formula, insert the values, clean it up a bit and fine-tune it to solve for the missing variable, and then just write your answer at the end. So formula, insert, fine-tune, answer. Okay. And we'll check back in about 5 minutes-ish. Actually, we'll go for like 6 minutes and see what answer we got. So I'll check back then. Meanwhile, I'm gonna just double check to make sure that the practice is available for you guys on the website. Okay, let me start with this question. So remember the first step, list all the values. So spring constant, I'll just write spring cons to shorten it, 520 newtons per meter. Stores 7.04 joules, that's an energy, so EPE equals 7.04 joules. How far is it extended? So extension, that's going to be my question mark. Write out the formula. Then substitute in from left to right. So EPE, checking my list, I do have a value for EPE, 7.04. Then 0.5, do I have a value for K, my spring constant? Yes, I do. My spring constant is 520. My extension is a question mark, so I'm going to leave it as just my letter. Then, cleaning it up a bit, remember any numbers that you can combine to make one number, do that first to make it like easier on the eyes and easier for you to rearrange. So 0.5 times 520, I'm just going to stick that into my calculator and get one number from that. That should be 520 divided by, times 0.5, that is 260. times E squared. Isolating the variable, I want to get rid of that 260, so I'm going to divide both sides by 260. I'm dividing because it got times on, so I have to do the opposite. Those 260s got cancelled. Now I just have to stick that into my calculator. 7.04 divided by 260. I'm gonna round it a bit. 0.027 is equal to E squared. Remember, we don't want E squared, we want just E. So to get rid of the squared, we do the opposite by square rooting, and we got to do that to both sides. So I'm square rooting the 0.027, and I'll round that to, so E is 0.16. So I just square rooted that in my calculator because, I mean, I don't know about you, but I can't square root 0.027 in my head. So my extension is 0.16 meters. And that's my final answer. Okay, so in the chat, I've linked to you guys the website again. If you go on elastic energy, if you click that, there should be a worksheet there. You obviously, because this is all optional, don't feel like you have to do all of this or anything like that. This is just practice available to you so you feel confident. The answers are at the very bottom, so on the next page over, those are the answers. So do whichever ones you can, and then check your answers on the next page over. And if you run into any problems where you just can't seem to work out how I got a certain answer or anything like that, feel free to email me or leave a comment on this video when it uploads, or you could leave a comment on Show My Homework. That's fine as well. But the idea is to just get as much practice as possible with the elastic potential energy equation. The one things to be careful of, remember, is obviously anything that is in centimeters, you want to change it to meters first because the formula takes it in meters. So you have to make sure all the units that are going into the formula are in the correct units. So for example, I see here question 3, it gave you an extension in centimeters. Make sure you divide by 100 to change it into regular meters. Another thing for you to be careful of with this particular in this particular elastic potential energy case is sometimes a question will give you old lengths and new lengths. Remember, don't just put old lengths or new lengths into the formula. You want to work out the change in the length. That's what the extension is, not the total length after stretching, not the length it was before stretching. You want the change. Right, so Louis, to answer your question, you might have seen on Show My Homework, because Mr. Rugg right now for year 9 is putting up the chapters that all of year 9 are doing on Show My Homework, and you might have noticed that he's put on atomic structure. Now you guys already did atomic structure, and we already took a test on atomic structure, so a lot of what you have to do now with Mr. Rugg is going to be revision. Later on, the next chapter after that is going to be the conservation and dissipation of energy. So if you're watching the stream, you're going to be ahead of the game compared to people who aren't following along, because then they'll have less practice and have to cram in all the calculations and everything in a shorter period of time. So in year 9 you will have the test on this as the next chapter after the atomic structure stuff ends in about 2 weeks. Then you'll have another 2 weeks on conservation and dissipation of energy, and then the test. on it. So you are actually, Louis, you are actually sort of stretching out the conservation and dissipation of energy stuff to being more than just 2 weeks, so you get as much practice as possible. So remember, don't have to worry about doing all of these. If you do like a few, like if you do 5 or something like that, and you feel like you're getting all of them right, and obviously we're all short on time right now. I know that with some of you guys, your workload might be high with all the different projects from different lessons. So once again, fit this to your schedule. The goal is just to make you feel a bit more confident and less worried and stressed about topics that you feel like you're struggling to do on your own at home. Okay, so it's just answers at the bottom here. If any of these you feel like, hang on, I have no idea how you got that answer, miss, send me a message, show my homework, email, or leave a comment, and I'll get back to you as soon as possible. Alright? Okay, so hopefully you guys have a good rest of the day. Enjoy yourselves, take care of your mental health, get some exercise in, and I'll see you next time.